On March 21, 1986, at the East Texas Cancer Center, a man arrived for a routine radiation treatment on a tumor in his back. A technician sat behind a shielded wall. She typed the patient's prescription into a terminal and pressed the key to proceed, executing a sequence she had performed thousands of times before. The screen flashed a short message, Malfunction 54. She had seen cryptic codes like this regularly. She pressed the key to clear the error and entered the command to fire again. But the beam had already fired. In a fraction of a second, the machine had delivered a massive, unshielded dose of electrons, roughly 100 times the radiation this man was meant to receive. The hardware had not broken. No physical component had snapped. The machine executed exactly the instructions it was given, masking a lethal operation behind a meaningless string of text. The error causing this massive overdose was not a new flaw introduced into this specific unit. The exact same code had been operating inside the previous model of this machine, the Therac 20, for years. In all that time, the older model had never harmed a single person. Yet between 1985 and 1987, this new model, the Therac 25, delivered massive radiation overdoses to 6 patients across the United States and Canada, resulting in multiple deaths. To understand why, we have to look at the manufacturer, Atomic Energy of Canada Limited, and the specific engineering choices they made when transitioning to the newer system. The Therac 25 became lethal because a single change to the machine's architecture gave dormant software defects an unobstructed path to the patient. To see how that path opened up, we need to understand the physics of a medical linear accelerator. This first mode projects a low-current electron beam directly downward for shallow tumors. The second mode produces X-rays, cranking the beam to 100 times normal power. To survive this massive increase, a dense metal target on a turntable physically slides into the beam's path, absorbing the violent stream and converting it into a safe spray of X-rays. The safety of the X-ray mode relies entirely on that physical object standing in the way. If the target is absent when the beam fires, an industrial-strength electron beam strikes the human body directly. On the left, the older Therac 20 relied on hardware interlocks, physical switches. If software fired incorrectly, these switches broke the circuit. On the right, the Therac 25. Engineers removed those mechanical interlocks, routing the connection directly from software to the firing mechanism. They reasoned that because the legacy software had never caused an accident in the older machines, the code itself was mathematically sound. By deleting the hardware interlocks, they stripped away the system's physical fault tolerance. Any undiscovered error in the code would immediately dictate the actions of the physical hardware. The Therac 25 software ran multiple tasks simultaneously, sharing data between a task that controlled the user interface and a separate task that physically configured the machinery. This architecture created conditions for a race condition. Picture an operator rapidly typing in prescription data, realizing she selected X-ray, and quickly editing the mode. The mechanical turntable required 8 seconds to rotate into position. If the operator edited the interface within that brief window, data synchronization broke. The software displayed electron mode, but the setup routine dropped the command, leaving the hardware locked on its high-power X-ray trajectory. The terminal now assured the operator the machine was in a low-power, perfectly safe state, while the physical components were aimed and primed for a high-power discharge without the protective metal target. A slow, inexperienced technician would never type fast enough to hit this strict 8-second window. The trigger required speed. The architecture actively punished human efficiency. An operator's muscle memory served as the catalyst for a lethal mismatch between digital state and physical reality. Even if that race condition had been fixed, a completely independent defect existed elsewhere in the code. This interface shows an 8-bit binary counter used by the machine's safety setup routine. Every time the configuration process ran, this single byte of memory ticked upward. The software contained a specific logic gate. It only verified safety components if this counter held a non-zero value. But when an 8-bit counter reaches its limit and ticks up, it overflows to 0. The logic gate reads the 0, assumes setup is complete, and bypasses the safety check entirely. If an operator pressed set in the exact millisecond the counter overflowed, the machine bypassed its own verification checks. Relying on a finite block of computer memory to control lethal physical forces proved entirely fragile. Both the race condition and the byte overflow ended with the exact same result, a terminal screen displaying Malfunction 54. This created a textbook case of the normalization of deviance. The operations manual defined Malfunction 54 merely as a dose discrepancy. It carried no indication of severity and gave no direction. The machine regularly threw cryptic errors, harmless bugs during normal operation. Staff viewed them as nuisances, clearing them to continue treatment. During the first accident in June 1985 in Marietta, Georgia, a woman received a massive burn. Hospital staff dismissed it as a localized anomaly, unlinked to the machine's operation. That disbelief was a direct consequence of the interface. The screen in the control room provided zero physical evidence that a catastrophic event had occurred to the patient in the adjacent room. A safety system provides no actual safety if it cannot communicate context. By constantly presenting minor bugs with the same visual weight as lethal failures, the interface actively trained operators to execute fatal commands. Because the units were spread across distant hospitals from Texas to Georgia to Canada, each accident appeared as an isolated, confusing medical anomaly, masking the broader pattern. When initial injury reports reached the manufacturer, technical management dismissed them. They insisted that an overdose was mathematically impossible under their model of the system. At the Tyler Clinic, a medical physicist refused to accept the second death as a coincidence. He spent hours trying to reproduce the Malfunction 54 code, attempting to break the machine's logic through sheer repetition. Working with the operator, he rapidly typed the exact sequence of keystrokes over and over. He matched the physical timing of the 8-second race condition, forcing the machine to output Malfunction 54 on command. Corporate assumptions of software infallibility collapsed only when a local engineer extracted the flaw from the code and produced undeniable, measurable data. The United States Food and Drug Administration ultimately intervened, forcing a total recall of the Theric 25 units. The primary corrective measure was a strict mandate to reinstate physical hardware interlocks. The manufacturer had to undo the exact design choice that defined the Theric 25. Subsequent analysis by software safety researcher Nancy Leveson showed the root cause was not a single bad programmer. The failure stemmed from a total lack of independent code review and inadequate system testing. The manufacturer had calculated equipment reliability based on the false assumption that software does not suffer from wear and tear, treating the code as inherently perfect. The Theric 25 accidents demonstrated that software cannot act as its own safety net. When the physical layer is removed, the system becomes entirely dependent on the perfection of the code, a standard that the development process never met. The older Theric 20 carried the exact same software bugs, but it never killed anyone, because the physical layer stood beneath the code, ready to catch the error. The legacy of the Theric 25 is a demonstration of the cost of removing physical interlocks. Trading hardware redundancy for software complexity removes the last line of defense between an invisible logic error and the patient.